Good evening, children.
Good evening,
Good evening, ma'am.
Good evening.
Good
Good evening, Bhavishya. Good evening, Danya. Good evening, Ritika.
Good evening, ma'am.
Good evening, Nandana. Good evening, Swati.
Good evening, ma'am.
Good evening. I've shared my screen, children. Is it visible?
Yes, ma'am. Visible.
All of you?
Yes, ma'am. It is visible.
Yes, ma'am.
Yes, ma'am. It is visible.
Okay, my voice is clear.
Yes, ma'am.
Yes,
All
ma'am.
right, children. Fine. So we will be starting off with the first chapter in our NCERT textbook, which is rational numbers. Before we understand the definition of a rational number, let's recall some other terms which we are already familiar with. All right. So I know you'd have guessed. All right. So what are natural numbers? What are natural numbers? Counting numbers are called natural numbers, right? Counting numbers. Counting numbers are called natural numbers. Are called natural numbers. Because, you know, on a table, if there are some objects lying on a table, okay, so there's a table and there are some objects lying on it. There are some objects lying on the table. Will you count 0, 10, 5, 3? No, we count in a particular order, right? We count in a particular order. We say 1. We don't start with 0. We say 1, 2, 3, 4, 5, 6, 7. So there are 7 objects lying on the table. So that's why we say counting numbers are called natural numbers, because that's how we start counting. It's from 1 we start counting. We don't count from 0. We count from 1. 1, 1, 2, 3, 4, 5, 6, 7. So there are 7 objects on the table, meaning counting numbers are called natural numbers. Counting numbers are called natural numbers. So natural numbers are represented. You can just write on this. Give the heading. Give the heading rational numbers.
Whole numbers.
Let me 1 second. Please give the heading rational numbers. Open your notebook. If you don't have a copy, just make a note in a rough book and you can make a fair copy later. Rational numbers. So under that, natural numbers. You must be quick in writing. Natural numbers. Counting numbers are called natural numbers. Counting numbers, should have started writing, are called natural numbers. And natural numbers are represented by the letter N. Natural numbers are represented by the letter N. So we can say N is equal to 1, 2, 3, 4. This collection is the collection of natural numbers. Natural numbers are represented by the capital letter N. And what you see within the flower bracket is the collection or represents the collection of natural numbers. Which is the smallest natural number?
1.
Which is the largest natural number?
That's endless.
We can't say, right? It's not, you cannot determine that. The largest number cannot be determined. The smallest number is 1. Okay. Whole numbers. Whole numbers. Write down, children. Natural numbers, including 0. Including 0 are called whole numbers. Natural numbers, including 0, are called whole numbers. Whole numbers are represented by the the capital letter W, 0, 1, 2, 3, 4. This is how we represent the collection of whole numbers. This is how we represent the collection of whole numbers. Whole numbers are represented by the capital letter W. Is that fine, children? Which is the smallest whole number?
0.
0 is the smallest whole number. Which is the largest whole number?
And cannot be determined.
Yeah, cannot be determined. Done, children? Finish writing?
Yes, ma'am.
Yes, ma'am.
Use the raise hand emoji. If you've all finished writing, use the emoji, raise your hand. If you finished writing. Danya, you're still writing, Danya? Danya, finished writing?
Yes, ma'am.
All right. What's the next term we are about to discuss? What is the next term? Yes. Natural numbers, whole numbers, then comes integers. Integers. The collection of all natural numbers. The collection of all natural numbers. 0 and the negatives. And the negatives of all natural numbers. Forms the collection of integers. Forms the collection of integers. Forms the collection of integers. Integers are represented by the letter I or Z. And we say like this. So -4, -3, -2, -1, 0, 1, 2, 3, 4, and goes on like that. So what do we see in this collection? Can you see natural numbers on this side, children? 1, 2, 3, 4 going on indefinitely. These are natural numbers. What is the negative of 1? -1. What's the negative of 2? -2. The negative of 3? -3. So you can see the natural numbers going to the right of 0. You can see the negatives of all the natural numbers to the left of 0. The negative of 1 is -1. The negative of 2 is -2. The negative of 3 is -3. The negative of 4 is -4, and so on. So in this collection of integers, we find all natural numbers, the negatives of all the natural numbers, and 0. This is the collection of integers. This is the collection of integers. See, we might all understand what integers are, but you should be able to express what you've understood. You might know what integers are, but how do you express yourself? This is how you express. It's the collection of all natural numbers. Children, am I audible and clear?
Yes, ma'am. Clear.
Yes, ma'am.
All right. So the collection of all natural numbers. See, you should get this picture in your mind. You don't have to memorize this. Nothing that you'll have to, read this many times. Just you should know the collection of integers. You must know the collection of integers. So these are the collection of integers. So what do you see in this collection? The collection of all natural numbers. Negatives of all the natural numbers and 0. That's what is in the definition. The collection of all natural numbers, 0, and the negatives of all natural numbers forms the collection of integers. Integers are represented by capital letter I or capital letter Z. And this is the collection. You don't have to do this, children. Don't do all this. Don't do this. Just write the collection. Write down fast.
Done, ma'am.
Okay. So you can see the natural numbers going on this side. You can see their negatives on this side, and you can see 0 here. So the collection of all natural numbers, their negatives, including 0, forms the collection of integers. Which is the smallest integer? Which is the smallest integer?
-4, ma'am.
Bhavishya. Yeah, which is the smallest integer, Bhavishya?
Ma'am, -4 and negative, ma'am.
Okay, so you're saying -4, but don't you think there's -5? Is this collection? This collection extends indefinitely on both the sides. The
Yes,
collection of integers extends indefinitely on both the sides. So do you think -4 is the smallest integer?
Yes, ma'am.
No? Then where is -100? Then where is -200, -300, -10,000, -1 lakh, -10 lakhs?
Ma'am,
Which is the smallest? Which is the smallest integer?
Ma'am, it is endless.
Mritika, which is the smallest integer?
Map infinite, not defined, ma'am.
Yeah, we can't say. We can't say. Correct. Which is the largest integer?
That's also not defined, ma'am.
Yeah, it's not determined. You cannot find out the largest. You cannot find out the smallest or the largest integer. But which is the smallest natural number, children?
1.
1 is the
One, ma'am.
smallest natural number. Yeah. Which is the smallest whole number?
0, ma'am.
0.
0. 0 is the smallest whole number. But the smallest integer cannot be determined.
And see the mic.
Yeah, you cannot determine, you cannot find out the smallest integer or the largest integer because the collection extends indefinitely on both the sides. Both the sides, the collection goes on. The collection is, it goes on this side and on this side. The collection extends indefinitely to the left of 0 and the right of 0. Bhavishya, which is the smallest whole number?
Ma'am, 0.
The smallest natural number?
1, ma'am.
The smallest integer?
Ma'am, it is endless.
Yeah, you can't say, right?
Yes, ma'am.
You cannot find out the smallest integer or the largest integer because the collection goes on and on to the left of 0 and the right of 0. Negative numbers go on endlessly to the left of 0 and the positive numbers go on and on endlessly to the right of 0, right side of 0, left side of 0. Okay, children, write down this. Write down this.
Ma'am, complete.
Are we still writing? All right, I'm clearing the slide. You must say, children, if you have not finished writing, you must tell me. Okay. Now, having recalled having recalled these terms, having recalled the terms natural numbers, whole numbers, and integers, now let us understand. See, I've used the symbols: natural numbers, whole numbers, integers, I or Z, integers. So now that we've recalled the meanings of these terms, you already know it. You just recalled it just to make sure that you've understood them correctly. Now let us understand what is meant by a rational number, or what is meant by rational numbers, whatever. Okay, rational numbers, or what is a rational number. All right. So if you can express a number in the form, it's very simple. See here, if you can express a number in the form A by B, or you can say P by Q, M by N, X by Y, whatever. If you can express a number in the form, let us say A by B. If you can put a number in the form A by B, where the numerator A is an integer, the denominator B is also an integer, but not 0. Because we know that division by 0 is not defined. See, when we say A by B, it's division. A divided by B. A by B is a fraction. See, now when we say 10 by 5, it's division. 10 divided by 5. This fraction indicates division. And division by 0 is not defined. 5 by 0. Division by 0 is not defined. Division by 0 is not defined. All right. So
Yes, ma'am.
when we say rational numbers, numbers of the form A by B, you should just get this, you should just picturize this in your mind. If you want to express, or you want to write what rational numbers are, you should just get this in your mind. A by B. What is A? Integer. What is B? Integer, but not 0. But not 0. You should just get this picture in your mind. And now using this picture, you should say the definition. Any number of the form A by B, or you can say I told you P by Q. Okay, so a number of the form A by B, where A and B are integers, and the denominator B is not 0, is called a rational number. Finished. If you can keep this picture in your mind, when you're asked to define the rational number, just write this in the corner of your book. Just write this in the corner of your book. Integer, not 0, not 0. Just write this. So now use this to define a rational number. A number of the form A by B. A number of the form A by B, where A and B are integers. Where A and B are integers and B not equal to 0, because the denominator should not be 0. Division by 0 is not defined. The numerator can be 0. The denominator should not be 0. A and B are integers. The denominator B not 0. B not equal to 0 is called a rational number. Is called a rational number. A number of the form A by B. Or if you can write a number, if you can express a number in the form A by B, where A and B are integers, B not equal to 0, is called a rational number. Got the definition, children?
Yes,
Did
ma'am.
we all get the definition?
Yes, ma'am.
Yes, Tanya. Define a rational number. Define rational number. Yes, Tanya. Try. Let me start for you. A number of the form. A number of the form. Okay, I've started for you. Tell me. A number of the form. What?
And can I tell?
Yeah, 1 second, Nandana. Danya, a number of the form?
A by B.
A by B. A number of the form A by B, where A and B are?
Integer.
Integers. Where A and B are integers. And B should not be equal to
0, ma'am.
0.
0. Is called a rational number. Is called a rational number. Yes, class, write down. You can say P by Q. Then you must say P and Q are integers. X by Y, anything. A number of the form A by B where A and B are integers, B not equal to 0 is called a rational number. Rational numbers are represented by the letter Q. Q.
Ma'am, is there a reason for why B is not equal to 0?
Swati, you were not in the meeting all the while, right?
Yes, ma'am. My phone got switched off, ma'am.
Sorry. Okay. Yes, Swati, I'll tell you. So division by 0 is not defined. Now, when you try to divide 0 by 5, okay, so 0 by 5, 0 by 5, you can finish the division. 5 zeros are, okay, let me take a different example first. Now, first write on this, children. 1 minute. Let's go in the order. We'll finish this. I'll come to you, Swati.
Yes, ma'am.
Yeah.
Yes, ma'am. Done.
Yeah, children.
Ma'am completed.
Yeah. All right, children. So now when we want to divide, supposing we have 12 by 3. Okay, so 12 by 3. So how do we divide? This 12 is the dividend. 12 is the dividend and 3 is the divisor. 12 is the dividend, 3 is the divisor. Always the numerator will go inside. The denominator will stay outside here. Always. It's not that the bigger number will be the, dividend. Somebody's mic is enabled. Please disable your mic. Unmute only when you want to say something. Otherwise, let your mics always be muted. The numerator is always the dividend. The numerator is always the dividend. The denominator is the divisor. So 12 by 3. 4s are 12, 0. So we say 12 by 3 is 4. The quotient is the answer. The quotient is the answer. 12 by 3 is 4. Now, when we want to divide 0 by 5, 0 by 5 is a valid expression. Supposing 0 is a numerator, whatever is the denominator, 0 by 5, 5. So 0 will be the dividend, 5 is the divisor, 5 zeros are 0. See, we are able to divide. We are able to divide 5 zeros are 0. Finished. So 0 by 5 is 0. See, we have to write the quotient, right? We always write the quotient. Let me show you again. We always write the quotient. The quotient is the answer. So now when we want to find 0 by 5, that is when the numerator is 0. See, when the numerator is 0. So the numerator is 0. The denominator is 5. So that comes out here as a divisor. 5 ones are 5. 5 ones are 5. 5 zeros are 0. The 5 zeros are 0. Finished. 0 is a remainder now. So 0 by 5 is 0. 0 by 5 is 0. But when we have to do 5 by 0, 5 divided by 0. It's 5 by 0. 5 by 0. See the tables of these 0 1s are 0, 0 2s are 0, 0 3s are 0, 0 4s are 0. So you don't know. You might say you can put 0 zeros are 0, but you have to find the number. Now when we divide like this, 0 and 5, we know that 5 zeros are 0, 5 ones are 5, 5 ones are 5. So we know, we see, I'm talking about this one now. We know we cannot use 5 ones are 5 because the number here is 0, but 5 ones are is 5. So if I say 5 ones are 5, the number is more than 0. So I cannot use this, so I have to use the previous one. So I'm using the rule of division. In division, what you do, you find the same number or a number just less than the dividend. You should get the dividend or a number just less than the dividend. So here 5 ones are 5. No, but I can't use 5 ones are 5. So okay, so the previous one, whatever is before that. So 5 zeros are 0. So 5 zeros are 0. So 0 by 5 is 0. 0 by 5 is 0 because you can divide. But in this case, 0 ones are 0, 0 twos are 0, 0 threes are 0. You cannot find anything from this, meaning you when you say 0 into 0, 0 into 1, 0 into 2, everything is only going to produce 0. So you cannot find the number. You cannot decide that since I cannot use this, I'm going to use this. Everywhere the values are 0. Now here, how did we decide? How did we decide here? 5 zeros are 0, 5 ones are 5, 5 twos are 10. So 10 we cannot use because it is 0 here. 5 also we cannot use because it's 0 here. So we take the earlier one. 5 zeros are 0. But in this case, you cannot decide at all because you cannot, everywhere it is 0. You cannot say that I cannot use this number, so I'm using the previous number. No, everywhere it is 0. 0 zeros are 0, 0 ones are 0, 0 twos are 0. Which is why we say the division by 0 is not defined. Division by 0 is not defined. When the denominator is 0, when the numerator is 0, yes, you can finish the division. 5 zeros are 0 and 0 is a remainder. But when the denominator is 0, you cannot complete the division at all because everything will produce 0. Will you say, okay, so now you say, have you finished writing the definition, children? I need to clear the slide.
Yes, ma'am.
All right. So now what we do? So we say, so one of you will say, one, so we all know this, 0 into 1 is 0, 0 twos are 0, 0 threes are 0, 0 fours are 0. Now there are five of you in the class. So I'm just going to take these 5 examples. So all the 5 of you are dividing now. Okay, so all the 5 of you are dividing. So one of you say, okay, 0, let me say 2s are 0 and complete the division. You cannot get the same number as the remainder. That also you know. You cannot, if the division comes to an end, you cannot get the same number as the remainder. That is one reason. But one of you will say 0, 2s are 0 and complete the division like this. So you will say 5 by 0 is 2. Another person will say, I did 0 tens are 0 and I got 5 as a remainder. So that means for that person 5 by 0 is 10. And another person will say 0 hundreds are 0 I did. So that means 5 by 0 is 100. There is no single answer. Everywhere it is going to be 0. When there is no one single answer, we say it is not defined. There should be one single answer. All of us should get the same answer. When you perform a calculation, all of us should get the same answer. If it is possible to get different answers, or if the answer is not unique, then we say it is not defined. When do we say it is not defined? When the answer is not unique. If all of us cannot get the same answer. If all of us cannot get the same value, we say the division is not defined. So here you can see, there is no single number as a quotient. So we say that division by 0 is not defined. There is no single answer for this.
Yes, ma'am.
Yes, children. Not defined. When any calculation is not producing a single result as the answer, all of us should get the same answer. Then it is defined. Then it is defined. 10 by 5 is defined. It's 2. 10 by 5 is defined. It's 2. 10 by 0 is not defined. So there's no single answer for that. So it's not defined. But 0 by 5 is 0 by anything is defined. 0 by 100 is 0. All of us will get 0 only. 0 by 100. 100 zeros are 0. Now, nobody will write 100 ones are, 100 ones are, 100 ones are is 100. So nobody will use this. All of you will do 100 zeros are 0 and finish it. So 0 by 100, all of you will say 0. So it's defined. But 100 by 0, as I just showed you, is not defined. Because there's no single value as the quotient. All right. Now it's time for me to check if all of you understood clearly. Is it fine so far, children? Natural numbers, whole numbers, integers, rational numbers. So Nandana, what picture will you take in your mind or will you get in your mind when you have to define rational numbers? Nandana.
Ma'am, A by B.
Then?
Both are integers, ma'am.
Okay.
If the B denominator should not be equal to the 0.
0. Now, Nandana, without looking to your notebook, don't look into your notebook. Tell me, define a rational number.
A rational number is a form of A by B where there is both integers and the B denominator should not be equal with 0.
Very good, Nandana. Very good. That's right. Ritika, repeat the definition in your own words. Ritika.
Yes, ma'am.
In your own words.
A number that forms A and B, where A and B are integers, B is not equal to 0, ma'am.
It's called a rational number.
Rational number.
B. Yeah, A by B. A divided by B. Not
Yes,
A and B. A by B. A divided by B. Now, is Mritika is 4 by 5 rational number? Is 4 an integer?
Yes, ma'am.
Let's have the collection of integers, okay?
Okay, ma'am.
Yeah. You know it goes on like this. It doesn't end with 5. Goes on. It goes on. These are integers. Am I right, children? These are integers.
Yes,
all right. Now, is 4 by 5 a rational number? How do we check if it's a rational number? The numerator should be an integer. The denominator should be an integer, but not 0. Does it satisfy the definition? Is the numerator an integer? Yes. Is the denominator an integer? Yes. It's not 0. So 4 by 5 is a rational number. 4 by 5 is a rational number because the numerator is an integer. The denominator is also an integer, which is not 0. So 4 by 5 is a rational number. Swati, is minus 100 a rational number?
Yes, ma'am. It can be written in the like minus 100 by 1. So it satisfies as A by B, ma'am. So it's a rational number.
Very good. Minus 100 is also a rational number because you can write minus 100 as minus 100 by 1. You can write minus 100 as minus 100 by 1, where minus 100 is an integer. You will find it here, somewhere here you will find it. Minus 100 is an integer. 1 is also an integer. Integer by integer is a rational number. Integer divided by an integer is a rational number. In simple words, you know, integer by integer is a rational number. Bhavishya?
Ma'am?
Is 250 a rational number?
Yes, ma'am.
Justify. How do you say it's a rational number?
Ma'am, we can put that 250 by 1 is a
By 1.
rational number, ma'am.
By 1? No, explain further. So 250 by 250 is 250 by 1. And what is 250? Is it an
Integer, ma'am.
It is an integer. You will find it on this side, on the positive side. And is 1 an integer?
Ma'am, it is also integer. It is not zero, ma'am.
0. Very good. So 250, though it is only 250, 250 can be written as 250 by 1. Integer by integer. So it's a rational number. Integer by integer is a rational number, which means all natural numbers and whole numbers, all natural numbers and whole numbers are rational numbers, and integers are rational numbers, because everything, see, if you take any natural number, all natural numbers, whole numbers and integers, this is the order in which we discussed. All natural numbers, whole numbers and integers are rational numbers. Because if you take a natural number, say 20 by 1, integer by integer, rational number. Whole number, any whole number, if you take 0 can be written with any denominator. 0 can be written as 0 by 1, 0 by 2, everything is 0, 0 by 3. 0 is the only integer which can take any denominator. See, now 20 is only 20 by 1, you cannot write 20 by 2. But for 0, you can write 0 by 1, 0 by 2, everything is 0, 0 by 3, 0 by 4, everything is 0. So 0 is also a rational number because you can write 0 as 0 by 1, for example, integer by integer, and the denominator is not 0. So 0 is a rational number, no doubt 0 is a rational number because 0 is 0 by 1. Integer by integer, it's a rational number. Similarly, if you take any integer, for example, any integer, supposing minus 33 is minus 33 by 1. Integer by integer, rational number. All natural numbers are rational numbers. All whole numbers are rational numbers. All integers are rational numbers. This is the order in which we learned. All these three are rational numbers. If they don't have a denominator, you can put denominator 1 and say it is in the form integer by integer, so rational number. Raise your hand, children. Lower your hands and raise your hand if you have understood. Lower your hands first. All of you lower your hands first. Yeah. Understood? Mritika, what's your doubt? Okay. So you have the definitions, natural. So now just finish it off by writing that under rational numbers, just complete this note, or you can just say important. Okay, you can just make a note of this. All natural numbers. No, let's not say all, we'll say natural. Okay. All natural numbers, whole numbers, and integers are rational numbers. This is very important. You should not make a mistake in this. In the exam, any question of this sort, you should not say only 1 mark I lost. I went wrong in answering this. Only 1 mark I lost. It's not about how many marks you lose. It's about how well you retain the concept. So even if it is 1 mark, it's a simple thing. So that shows that you did not take the initiative to remember even this little thing. So that will only talk about your responsibility. 1 mark. And so 5 is a rational number, and you say I went wrong in answering that. I said no, I said false, and I lost 1 mark there. That's a big mistake. Okay. So all natural numbers, whole numbers, integers are rational numbers. Shall we proceed, children?
Yes, ma'am. Done.
Yes, ma'am.
Write down, children. Properties of rational numbers. Please write down what you see on your screen. Properties of rational numbers and write down all those three. Closure property, commutative property or commutativity, associative property or associativity. Commutativity, associativity. Done, children?
Ma'am, 1 minute, ma'am.
Yeah, okay. Properties of rational numbers.
Ma'am, completed.
All right.
Done, ma'am.
Yeah. Done, children?
Yes, ma'am.
All right. So closure property. These you have to take, we'll understand. It will take time for you to write down all this in the class. So you can, once we understand, you can take a screenshot and complete it in your classwork later. Please maintain a separate book. Don't pick different books for every class. Maintain one book, preferably a new book and preferably a ruled book. So maintain one book for this class. If it's ruled, it'll be more organized. Your writing will be more organized. You'll be writing on the line, so it'll look more presentable, neat. Use a ruled book, preferably long, new, long, ruled. All right. Yeah, so, and please be responsible. Write down everything I ask you to write in the class. Now we're all high school students. So we must be, responsible as the term says, high school students. All right. So now children, let's understand this. So we'll understand if whole numbers are closed under addition, subtraction, multiplication and division. See, we will check the closure property. Now you don't know what closure property is. I'm still to tell you. We'll check the closure property on whole numbers for all the four mathematical operations. Addition, subtraction, multiplication, division. These are the four mathematical operations. We'll check this property, this closure property on whole numbers for all these four operations. Okay, so now I'm just trying to tell you what we are going to, be doing. So we'll check the closure property on whole numbers, natural numbers, integers, and rational numbers. That's what we've discussed, right? We have discussed natural numbers, whole numbers, integers, and rational numbers. These are the four terms we saw just now. So we'll check this property on all these four numbers: whole, natural, integers, and rational. So we'll check this property. See here, this is the first slide on whole numbers. Second slide is on natural numbers. Then is on integers. The same property, closure property on integers for all the 4 operations. And then on rational numbers. So with this, we finish the closure property. Then the next property, mutativity. So like that, that's what we'll be doing. You got some idea? No idea?
Yes, ma'am.
Children, please answer.
Yes, ma'am.
All right. Okay. Now closure. Now when we say, so you can see here, you can see in the remarks that whole numbers are closed under addition. Okay, so you see here, whole numbers are closed under addition. What does it mean? That means the sum of 2 whole numbers will always produce a whole number. See, whole numbers, keep only that collection in your mind. Now, closure property of whole numbers with respect to addition means when we say that whole numbers are closed under addition, see the remark there, whole numbers are closed under addition. We mean that when we add 2 whole numbers, the sum, that is the answer, sum meaning the answer, is also a whole number. Let's check that. So whole numbers. What are whole numbers? Let me write the collection 0, 1, 2, 3, 4, 5. It goes on like this. OK, this is the collection of whole numbers. Whole numbers are closed under addition means when you take any 2 whole numbers. OK, let's say 0 and 25. What's the answer you get? 25. Is the answer, is this answer also a whole number? Yes. When you consider any 2 whole numbers and you find their sum, the answer or the sum will also be a whole number, always be a whole number. That means whole numbers are closed under addition. Okay, the sum of 2 whole numbers is always a whole number. That means whole numbers are closed under addition. That's what we mean by saying whole numbers are closed, closure property, closed under addition. Now let's check if they're closed under subtraction. You can see the remark there, whole numbers are not closed under subtraction. Because when see, it should always be true. Even if one thing is false, that means they're not closed. Now let me consider the whole numbers 2 and 10. Is 2 a whole number? Yes. Is 10 a whole number? Yes. Now let me find the difference. 2 minus 10. What's the answer? Minus 8. Minus 8 is not a whole number. That means whole numbers are not closed under subtraction. See, now you may say that I took 13, I took 7, I subtracted the 2 numbers and I got 6 and 6 is a whole number. Fine. You may get a whole number sometimes, but not always. When you say they are closed, that means they should always be a whole number. The answer should always be a whole number. Even if there is one exception, it will be not closed. The difference of 2 whole numbers is not always a whole number. The difference of 2 whole numbers, you have it here, children. Don't worry. See here, I have whatever I'm saying is all here. So just understand that's what is, that's what you have to do now. The difference of 2 whole numbers. The difference of 2 whole numbers need not always be a whole number. So like, for example, you might say 100 is a whole number and 25 is a whole number. I subtracted, I got 75, which is also a whole number. Fine. But if you do the other way, 25 is a whole number, 100 is a whole number. I subtract, the difference is minus 75, which is not a whole number. It's an integer. That means whole numbers are not closed under subtraction because the difference of 2 whole numbers is not a whole number. It's not always a whole number. Do we understand that, children?
Yes, ma'am, understood.
Yeah. Now multiplication. That means when you multiply two whole numbers. 1 second, children, I'm getting a call. Just a second. Read the slide till then. Children, excuse me. So sometimes, some calls I'm not able to avoid. I had to just attend this call. Sorry. Back quickly. Am I audible?
Yes, ma'am.
Yeah, children. So multiplication, when you take any two whole numbers, okay, so whole numbers, let always just write the list like this so that you don't get confused. This is the list. It's endless. So when you take any two whole numbers, so supposing I take 0 and suppose I take 5. The product is always a whole number. 0 into 5. The product of two whole numbers is always a whole number. Yes, you take any two numbers, 3 and 4. The product will always be a whole number. Take any two whole numbers. Anything. So some 121 and 3. This is a whole number. This is also a whole number. The product will also be a whole number. It's a whole number. So when the product of two whole numbers is also a whole number, that means whole numbers are closed under multiplication. Closed meaning you must get, when you're working on whole numbers, the answer also should be a whole number. When you're working on natural numbers, the answer also should be a natural number. That means they're closed under different operations. Now division. Are whole numbers closed under division? Now supposing you, again, don't forget this collection. Now let's divide. Let's divide 3. 3 divided by 2. What is 3 divided by 2? 3 by 2. 3 by 2 is not a whole number. Now supposing whole number 15, whole number 3, whole number 15, whole number 3. We divide. The answer is 5. It's a whole number. It is a whole number sometimes, but not always. When you divide two whole numbers, the answer should always be a whole number. Then that means they are closed under division. No, here always you will not get a whole number. Sometimes we get a whole number. Now, for example, 20 is a whole number. 5 is a whole number. 20 is a whole number. 5 is a whole number. When I divide 20 by 5, I get 4, which is also a whole number. Okay, here it works. But if I take 33, whole number 33, and I take whole number 27. So I get 3 11s or 3 9s. 11 by 9 I get. 11 by 9 is the answer. And 11 by 9 is not a whole number. That means whole numbers are not closed under division. They are not closed under division. Do we understand, children? That means the quotient of two whole numbers is not always a whole number. Sometimes it's a whole number. Sometimes it's not a whole number. So whole numbers are closed under addition and multiplication, but not under subtraction and division. You should write your own examples. I'm not writing the examples here. You must write. I told you what is closed. So you should write your own examples. Now you must write an example for not closed under subtraction. So when you're filling this table by yourself, you must write examples like this. So you should say like I take 30 and I take 100 and I subtract the 2 and I get minus 70, which is not a whole number. So whole numbers are not closed under subtraction. Just give one example like that. The space for you is to give examples to justify this one, to justify the remark. So for division also, what example will you give? You must say now 6 is a whole number, 10 is a whole number. When I divide 6 by 10, I get 3 by 5. But this is not a whole number. This is a whole number, this is a whole number, but the answer is not a whole number. So they are not closed under division. Do we understand that, children?
Yes, ma'am. Understand.
Yes, ma'am. Yes, ma'am. Understand.
So whole numbers, closed meaning when you add, when you take whole numbers, when you take two whole numbers, when you add, subtract, multiply or divide, if you get the same, not the same, if you get a whole number itself as the answer, they are closed. If you don't get a whole number as the answer, they are not closed. That's all it is. When you take two whole numbers and you add them, subtract them, multiply them, divide them, and you get the answer also as a whole number, that means they are closed. If you don't get a whole number as the answer, they are not closed. So take a screenshot of this table, children, and complete this table. Here in this table, you should just give examples for you to understand. Think and give examples here. 1 or 2 examples. Take a screenshot and complete this. Yeah, complete this. Make a table like this and complete this in your classwork.
Completed.
Yeah. Excuse me. So see here, we say that whole numbers are not closed under subtraction. Why? Because that is for any two whole numbers A and B. If you take any two whole numbers A and B, A minus B, the difference need not always be a whole number. Sometimes it's a whole number, sometimes it's not a whole number. For any two whole numbers A and B, if you take any two whole numbers A and B, A minus B need not always be a whole number. That's why they're not closed under subtraction. Similarly, for division, if A and B are two whole numbers, when you divide A and B, A by B need not always be a whole number. So they're not closed under division. Take a screenshot, write this in your book.
Ma'am,
Yeah.
ma'am, your voice is not audible, ma'am. It's breaking.
Let me check with the others. What about Bhavishya, Nandana, Swati and Ritika? Am I clear?
Ma'am, it is clear.
Clear only, ma'am.
One by one,
The
Ritika,
voice is
is
not
clear?
Ma'am, it's clear.
Nandana,
And for me, it's clear, ma'am.
Swati and Bhavishya?
No, ma'am, your voice
Ma'am,
is
it
not.
is clear, ma'am.
Ma'am, I think she has network issue.
If it's not clear, Lisha, just leave the meeting and join again. Just check that. Leave and join again. Danya? So it looks like she has a network issue. She's not able to join. Okay, we have to continue. So now on natural numbers, children, same idea. Closed means closure property means now again natural numbers. When you take two natural numbers and add, subtract, multiply or divide, the answer also should be a natural number. It should not be a whole number. It should be a natural number. When you consider two natural numbers, what is this closed? What do we understand by closed or closure property? So when you perform that on natural numbers, it means when you consider two natural numbers, their sum, difference, product, quotient also should be natural. If it is natural, it's closed. If it's not natural, it's not closed. That's all. Do we understand the closure property, children?
Yes, ma'am.
Yes, ma'am.
So when you're working that on whole numbers, the answer should be a whole number. Yes, Lisha. Oh, you're not Lisha, sorry, you're Danya.
Ma'am, audible, ma'am.
Now it's audible. It's clear.
Yes. Yes, ma'am.
Yeah, that's what. Okay, so when we test the closure property on natural numbers, you will again see that they are closed under addition and multiplication, but not under subtraction and division. Not under subtraction and division. All right. So again, see here, that is The sum of two natural numbers. When you take a natural number and another natural number, when you add, it will always be natural. But the difference, natural number minus natural number, will not always be natural, will not always be a natural number. N into n is always a natural number. But n divided by n will not always be n, will not always be n. When you add n plus n, I hope you understand the short forms. N plus n, natural number plus natural number will be a natural number. So it's closed under addition. Multiplication also, when you multiply two natural numbers, the product is also a natural number. But when you find the difference of two natural numbers, for example, like we did for whole numbers, children, nothing new here, just that you should not take 0. So when you take a natural number like 30 and 50, the answer you get is minus 20, which is not natural. Product will always be natural. The quotient, like we did for whole numbers, 100 divided by 101. 100 is a natural number. 101 is a natural number, but 100 by 101 is not a natural number. But sometimes, like when you do 45 by 15, 45 is a natural number, 15 is a natural number, the answer is 3. That's also a natural number. Okay, sometimes we get, but not always, right? So they're not closed. They're not closed under division. So in simple words, n plus n is always n, n. N minus n is not always n. N into n is always n, N divided by n is not always n, I hope we understand what I mean, children.
Yes, ma'am.
Yes, ma'am.
Yes,
Yeah,
ma'am.
so natural numbers are closed in addition and multiplication, but not under subtraction and division. It's not difficult to remember. Just take examples. That's all. You must just be familiar with the terms. Closure property means what? You should not get confused between the different properties. So this is closure property. When you do it on natural numbers, all operations, if you do on natural numbers, you must get the natural number as the answer. If you get, it is closed. If you don't get, it's not closed. Let's go to the next one. Take a screenshot, children. Take a screenshot like this. Yeah. Complete this in your book. Please take a screenshot of this one also.
Done, ma'am.
Yeah. Please write this. See, when you write it, you can retain it better. Now on integers. So again, if you check on integers are what? Like -5, -4, -3, -2, -1, 0, 1, 2, 3, like this. This collection integers. So the sum of two integers is always an integer. If you take -5 plus -6, the sum of two integers is always an integer. The sum of two integers is always an integer. The difference of two integers is always an integer. The difference will always be an integer. Because you find the difference, if you take -6 and minus some -30, what's the answer? -6 plus 30, which is equal to, 6, no, I wrote 60. Okay, let me make this 60. So -60 plus 30, which is -30, which is an integer. Integers are closed under subtraction. Because here you have the negative numbers also, right? So when you subtract any two integers, the answer will be an integer. Because the answer can be negative or positive, or it can be 0 also. So we have a wider range We have a wider range here. Yeah. Again, when you try, you can do all this. When you multiply two integers, the answer is always an integer. For your example, like anything so difficult to pick. So into 0 is 0. Integer into integer is an integer. But integer by integer is not always an integer. Like we have done earlier. If you take the integer like 5 and another integer -4, so which is -5/4. It's integer by integer, but the answer is a rational number. It's not an integer. The answer is a rational number. It's not an integer. So like this, you can give many examples where it is not an integer. Division of two integers is not always an integer. Division of two integers is not always an integer. It is sometimes an integer, sometimes not an integer. That means integers are not closed under division. Take a screenshot, children. So integers are closed under addition, subtraction, multiplication, but not under division. Because when you divide two integers, the answer may be an integer, may not be an integer. So they are not closed. The answer is not always an integer, so they're not closed. Is that fine, children?
Yes, ma'am. So if we divide and the answer is in the form of a by b, it's not an integer.
It's not an integer, no? Because yeah, when the answer is now when you suppose -6 by -7. 1 minute. Yeah, so supposing -6 is an integer, -7 is an integer, -6 is an integer, -7 is an integer. We are trying to divide. So this is nothing but 6/7. There's nothing but 6/7. 6/7, the answer 6/7 is not an integer. The answer 6/7 is not an integer. It's a rational number. When you're performing closure property or when you're checking closure property on integers, the answer should be an integer. If you're checking on natural numbers, the answer also should be a natural number. So -6, for example, -6 by -7 means minus and minus cancels. So 6/7. 6/7 is a rational number. Integer by integer is a rational number. It's not an integer. You can see 6/7. Okay. Now, how do you understand if it is an integer or not? What did we understand about integers? Integers are natural numbers. Integers, you should check on three things. The integers will be natural numbers, or it will be negatives of natural numbers, or 0. It should be one of these three. Then only they are integers. Integers means they should fall under three things. Either it should be an integer means it should be a natural number. Okay, if it's not a natural number, it should be the negative of a natural number. Okay, it's not that also, then it should be 0. One of these three it should be, then only it's an integer. Otherwise, it's not an integer. So 6/7 is not a natural number. It's not the negative of a natural number. It's not 0. So 6/7 is not an integer. It is a rational number. Swati, am I clear?
Yes, ma'am.
Okay, that was your question, right?
Yes, ma'am.
All right. Take a screenshot, children.
Yes, ma'am.
So integers are closed under addition, subtraction, multiplication, and not division. Take a screenshot of this. This is just theory for you to understand better. When you write this, you will know how to express. All right. Now, closure property on rational numbers. Closure property on rational numbers. So see there, they are closed. Actually, rational numbers are closed under all the operations. For division, it's not closed. If you exclude 0, it is closed. If suppose from rational numbers, if you take away 0, then it is closed everywhere. Rational numbers are closed under addition, subtraction, multiplication, and division. If you take away that 0, it is closed under division. If you take, because 0 is a rational number, right? If you include the rational number 0, then it is not closed. If you don't include the rational number 0, then it's closed. Okay. So again, see, we are dealing with a closure property. That means whatever number you're taking a rational number. The sum of two rational numbers should be a rational number. The difference should be a rational number. The product should be a rational number. The quotient should be a rational number. Rational number means integer by integer. Rational number means integer by integer. So you have a wider collection. You can get so many different things as the answer. You have a wider collection. See, when you work with natural numbers, less collection. Whole numbers had 0. Again, less collection. Integers, the collection was a little more. And rational numbers, the collection is still more. That's why it's closed here. Under addition, subtraction, multiplication, and also actually under division, but except for 0. So examples, children. What we mean by this property, a rational number. Rational numbers are represented by the letter Q. Integer by integer is a rational number. Okay. Integer by integer is a rational number. Rational numbers are represented by Q. Don't get confused. Rational number means integer by integer is a rational number. Is a rational number. So when you add two rational numbers, the answer is rational. See, like you add 1 by 2 and 3 by 4. Or why so complicated? 1 by 2 and 3 by 2. The answer is 4 by 2, which is 2. Which is 2 by 1. It's rational. Anything, you take two rational numbers, the answer, when you add, the answer is rational. Similarly, when you subtract two rational numbers, the answer is always rational. See, your collection is more. The rational numbers means they can be 0, negative, positive. It can be fraction. In rational numbers, you have more collection of numbers. They're closed under subtraction. They're closed under multiplication. When you multiply any two rational numbers, see, like you multiply 4 by 5, this is a rational number, and you multiply, say, something like 30 by something like 20. Okay. This is a rational number. This is a rational number. This is also a rational number, Q. So 4 ones are 4 5s are 20. 5 ones are 5 6 are 30. So 6 by 5 is the answer. 6 by 5. Rational number. The answer is a rational number. Integer by integer. So rational numbers are closed under multiplication. And rational numbers are also closed under division. See here, if you divide any number, say minus 25 by minus 27. It's a rational number. Minus 25 is a rational number. Minus 27. See, we know that even minus 25 is a rational number, children, because minus 25 by 1. Minus 27 is rational. When you divide, the answer is 25 by 7. Sorry, 25 by 27. Which is integer by integer. Integer by integer. It is rational. When you divide two rational numbers, the answer is also a rational number. But the 0 is there. So because of the 0, okay, so because of 0, now what does the 0 do? Now what happens when you say 0 by 5? The answer is 0. 0 by 5. Rational number by rational number, 0 by 5. The answer is 0, which is also a rational number. But when you do 5 by 0, it's not defined. Division by 0 is not defined. That means only when you divide by 0, since it's not defined, we say rational numbers are not closed under division. Just for this, we say they're not closed. That's why I've written the note below. However, if we exclude 0, then the collection of all natural numbers is closed under division. So remember that rational numbers are closed everywhere. Addition, subtraction, multiplication and division. When you add two rationals, you will get rationals. When you subtract, you get a rational number. When you multiply, divide, everywhere rational you will get. The answer will be rational. But because of the 0, rational numbers are not closed under division. Because division by 0 is not defined. You don't get a rational number as the answer. It's not defined. Just for this, rational numbers are not closed under division. If you take away that number 0, you can't do that. Except 0, the rest of the collection of rational numbers are closed under division. Yes, children, take a screenshot of this one.
Took already, ma'am.
This one.
Last point I can't see, ma'am. No, next slide, that last point, ma'am.
Now?
No, ma'am, that division, that line, ma'am. Last line.
Previous slide or this slide, ma?
Ma'am, this slide only, ma'am.
Last line, why you can't see? 1 minute. Why, Bhavishya?
Ma'am, because that video, that and all, it is hiding that, ma'am.
Oh. Oh my God, 1 minute. Have you all pinned my window?
Yes, ma'am.
Yes, ma'am.
Okay, no, because we are used to online classes now. I did not give that instruction. Have you all pinned my screen?
Ma'am, automatically.
Okay,
Yes.
okay.
You're starting a screen.
Okay, if you've pinned my window, I don't know why you're not able to see the last one. Read the last one. What is it you can't see? Just read it.
Ma'am, I can see, ma'am.
It's okay.
We can say
And
that
I can also
rational
see.
numbers are closed under addition. This for
Bhavishya,
any
louder,
two
Bhavishya.
rational
Bhavishya, louder.
Ma'am, that last one, the after that is for any two rational numbers A and B. A divided by B need not always be a rational number. After that point, ma'am.
After that, okay. I'll share that picture then on WhatsApp with you.
Okay, ma'am.
Okay, I'll share the picture.
Okay, ma'am.
What is today's number?
Is it over, children? Is this over?
Yes, ma'am.
Now let's sum up here. Now what did we do? What did we understand? We understood the closure property. We understood the closure property with rational numbers, integers, whole numbers, and natural numbers under all the different operations. What we learned separately, no? Now we are summing up in a table. So see here, how do we understand this table? See here, rational numbers are closed under addition. I don't know. You must say yes or no. Now in this table, what you should fill is yes or no. Yes, no, yes, no, like that. That's what you should fill. That's what you should fill in this table. Now, how do we understand this table? Whatever we have learned so far, we have summed up in this table. Rational, you should read like this: rational numbers are closed under addition. Yes or no, you should write here. Again, rational numbers are closed under subtraction. Yes or no? That's what you should write here. Don't write yes or no. You must write yes or no. One answer. Don't write yes or no. Again, rational numbers.
Should there be example?
Rational numbers are closed under multiplication. Rational numbers are closed under division. You must write yes or no. Again, like for the last one, you see, natural numbers are closed under addition. Yes or no, you must write here. Natural numbers are closed under subtraction. Yes or no, like that. Do we understand this table?
Yes, ma'am.
Yes, ma'am.
Yeah. So you must sum up in this table.
Should we have to give example?
Swati, louder.
Should we have to give example?
No example. Just write yes or no. You can scribble the example in the rough column and then you will come to a conclusion. No, yes or no. Just write yes or no. That's all.
Yes, ma'am.
All right. Have you have you all started 8th standard at school? All of you?
No, ma'am.
No, ma'am.
No, ma'am.
Who started?
Ma'am,
Nobody?
Swati started to go school.
Okay. Swati, I always get confused. Now, Swati is from Kamala Niketan, right?
Yes, ma'am.
Nandana is also from Kamala Niketan, right? Oh, Nandana is from CARE. No, not CARE. Kaveri Global, right, Nandana? I can't hear Nandana. Nandana is from Kaveri Global, right? Okay, okay. Bhavishya Vagisha Vidyashram.
Yes, ma'am.
And Danya is from Green Park, right?
Yes, ma'am.
Pratika Z School. All right. So only Swati has started 8th standard at school. Okay. So, see children, sometimes to save time, you have to write some content at home. Now, I'm giving you this time, it's going to be, don't get scared. This chapter has a lot of, this theoretical stuff than the numerical ones, a lot of theoretical stuff. So I'm just giving you this as homework because our next class will be on Monday. You have the weekend of Saturday, Sunday. A little extra work I'm giving you. Please complete all this. We'll understand this in the class. Just make all this table. Make all this table and keep it ready. Take a screenshot, children. Commutativity, we have not understood. We are still to discuss this, but just finish this in your notebook. Just make this table in your notebook. Is it over?
Yes, ma'am.
Now, I say you can write it, but if your parents feel write it only after understanding, then don't write this. Leave some space in your book. I say you can just finish it so that later you can read and understand once I explain. But if your parents feel don't write it before understanding it, don't write it. Just listen to what they say. From my point of view, you can just complete this in your book so that we can understand the class later. So this is the first one. Second one, quickly take screenshots.
Yes, ma'am.
3, this one, so commutativity on natural numbers. Commutativity on natural numbers. This is the description.
Yes, ma'am.
So when you write this, write it consciously, meaning understand what you're writing. So in the class, you can discuss and ask doubts better on Monday. You will understand. It's not new. You can follow this. Now, the same property, commutativity on integers. Commutativity on integers. Done?
Yes, ma'am.
Commutativity Description. On integers, description.
Yes, ma'am.
Class, all of you?
Yes, ma'am.
No, don't request for these later, ma. It's difficult to send all this on WhatsApp. I can show you now in the class. All of you?
Yes,
ma'am.
taking it, ma'am.
Okay. Now the next one. Commutativity on rational numbers. Commutativity on rational numbers.
Yeah, ma'am, done.
Yeah. Description.
Yes, ma'am.
Danya, you taking screenshots, Danya?
Yes, ma'am.
All right. Yeah, this is summing up. Commutative for all the four numbers, rational, integers, whole numbers, natural numbers. You can see the four operations. You can see the four types of numbers, rational, integers, whole, and natural. And the four operations. Commutative for. We're summing up all that we understood about commutativity in a table. Next, associativity. That's all. With this, the properties come to an end. Associativity on whole numbers.
Yes, ma'am.
Yeah. Description on whole numbers, description.
Yes, ma'am.
Bhavishya, are you comfortable, Bhavishya? Are you following me?
Yes, ma'am, but all of these description, that last line I'm not able to see, ma'am.
Why, darling? Oh, why? Not if you get it. Are you on a phone or a laptop?
Yes,
you on-
ma'am.
You are on a phone or a laptop, ma?
Ma'am, laptop, ma'am.
Last line. What about the others, children?
And I can.
Ma'am, it's visible.
And I
The
think
slides are.
I think that the taskbar you have not. That's enabled. I think that is hiding the last line.
And how we
Yes,
can
ma'am.
zoom the screen now.
Oh, you should get it out of your screen. That's what it is. How can I help you?
Since all our names will be in
The last
red,
line, no, everywhere.
I think
Okay, let me see. You just write whatever is visible, Bhavishya. I'll just think what I should do.
Okay, ma'am.
Yeah. Children, associativity on natural numbers.
Yes, ma'am, done.
Description.
Yes, ma'am, complete.
Integers. Associativity on integers.
Ma'am, please show me that before slide, ma'am.
Yeah. Integers. Associativity on integers.
Done, ma'am.
Yeah. Description.
Done, ma'am.
Done, children. Next one. Associativity on rational numbers.
Yes, ma'am.
And description.
1 minute.
Yeah. Previous slide.
Ma'am, 1 minute, ma'am.
Yeah. Yeah, next one.
Ma'am, before slide, ma'am.
Okay,
I'm
okay. Associativity on rational numbers.
taken, ma'am.
Yeah. Description.
Yes, I'm done.
Yeah. We are summing up associativity property or associativity. Associative property or associativity for the different operations on the different numbers.
Yeah,
We have 4 different numbers. We have 4 different operations. The 4 different operations are addition, subtraction, multiplication, and division. So we have 4 different operations. We have 4 different numbers, rational, integers, whole, and natural. And we're checking the property, associative property on these 4 numbers for the 4 different operations. Yes, children. All right, children, I know I took a little extra time because I was caught up on that call, so I had to finish this today. All right, children, so that's it for today's session. Thank you so much. Good night. Please complete your work by the next class.
Thank you, ma'am.
Every class you will not get so much to write. Don't get scared. Now, since your school has not started, I thought you have time to write. So we can do more in the class. All right,
Thank you, ma'am.
Yeah, thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, children. Good night.
Good night, ma'am.
Good night.
Yes, ma'am.